Hi, I'm Roger Stenbach with PreciseRF. Today we'll cover the new TDR-CableScout. The TDR-CableScout is a device that allows you to measure and test transmission lines and cables, especially for the ham radio world. Now, before we go any further, let's understand that at this particular time, we need to have some understanding of the fundamentals of TDR, and we'll cover those first before we go into the nuts and bolts of this particular demonstration. This will take about 10 to 15 minutes. Now, to do all of these tests, you're probably wondering what this box is all about. Well, you understand that cables are sometimes unruly and not very practical in the studio, so that's why we're using this box. It has all the cables built in, and we can simulate all of the faults. Now, all the information that we're covering today is also covered in our applications book. You can get this free online, or you can order the actual book from us directly. Okay, let's get going. Hi, Roger Stenbach again here. Let's get going on the TDR fundamentals. All right, first concept are transmission lines. The ideal transmission line matches the transmitter and the antenna and delivers all the energy without any losses. This occurs only when there are no reflections or losses. Now, in the real world, transmission lines always have losses. All right, continue. Now, these are the sources of line losses. You've got yourself some dielectric, resistive, and reactive losses. You've got some manufacturing defects, poor quality, environmental damage, UV radiation, moisture, and sometimes just kinked and broken cables. All right. Now, here's a simple TDR system. Nothing more than radar applied to cables. So we have a pulse generator that's connected via a T connected to an oscilloscope, high impedance input. And we have a pulse that's injected, it's called the incident pulse, into the cable. And the pulse and any reflections are then displayed on an oscilloscope. So here's a block diagram. As you can see, we have a fast rise pulse generator, an oscilloscope, a T connector, and the device under test, the DUT. So we send that pulse out, look for reflections, and measure the round trip time, and we can tell you where the fault occurred. All right. The simple TDR system characteristics are low cost. It requires a T connection, which is maybe inconvenient, and it uses the scope's high impedance input, which slows down the rise time. It's got lower resolution, and all your calculations have to be done manually. Now, here's the CableScout TDR system. You notice that the actual CableScout is right here, and here's our oscilloscope. This system has a separate RF microwave sampler, which takes a look at the device on the test port. All right. However, the CableScout system, a very good system. It costs more. It uses a dedicated microwave sampler. It uses the scope's 50 ohm input impedance, which results in much faster rise time. It has higher resolution, and the computer makes all your calculations, and that is very, very handy. Now, the oscilloscope also has some requirements. The scope should have a calibrated vertical and horizontal time base. The bandwidth should be of sufficient high characteristic to identify reflections. And for short line distances and circuit board TDR, a finer time resolution is required. So resolution, as you remember, is a function of the scope's rise time. Now, we know from prior study that a common mathematical relationship between bandwidth and rise time is such: bandwidth equals 0.35 over the rise time in nanosecond, or rise time equals 0.35 over the bandwidth in megahertz. So for ham radio work, a 1 to 200 megahertz oscilloscope is all you really need. Now, here's what it looks like. Here's a 20 megahertz oscilloscope. You can see it right here. 20 megahertz, rise time 15.3 nanosecond. All right, here is a 100 megahertz scope, and you see that it has a 5.3 nanoseconds. And finally, here's a 200 megahertz scope, and you see that the rise time is 2.9 nanoseconds. All right. Now, the effects of rise time on TDR resolution. You took a piece of 12-foot piece of coax, RG58, and it had a published velocity factor of 0.66. We'll talk about that in a minute. And that's about the shortest cable that can be tested with the 20 megahertz oscilloscope. Now, impedance variations, as you'll see in these pictures coming up, are clearly visible in the 100 megahertz to 200 megahertz scope. All right, here's the 20 megahertz scope, and you can see that the rise time is stretched out, and you can barely make out this TDR reflection right here. Now let's take a look at a 100 megahertz scope. Again, now we get to see some resolution in these slight bumps right here. And of course, here's a 200 megahertz oscilloscope, and there you can starting to see the actual connectors that are connecting the cable to the TDR system. Now we know that the speed of light is approximately 300,000 kilometers per second, but the propagation through cables isn't quite that high. It's about 0.66 to 0.9, depending on the cable, of the speed of light. So to locate the distance to the reflection, we need to measure the round trip time, and then we can actually find the distance where the fault is located. Now the incident pulse, is what they use in TDR work, is the pulse applied to the device under test. And the amplitude is always measured from the most negative level to the most positive level. Now the reflected pulse contains signals which are made of reflections. And these are caused by reflections such as variations in line impedance, they call it ZO, not matching the pulse and generator source impedance, ZS, and the amplitude is always measured from the most positive level of the incident pulse. Now, on a properly terminated line with a uniform impedance, the entire transmitted pulse will be absorbed at the far end termination, as you see in this picture. Now, if you have an open transmission line, it represents a very high impedance, so this creates a reflection. You can see that reflection right here. In a shorter transmission line, it represents a very low impedance, and it also creates a reflection, but it's opposite in polarity, so it looks like this. Okay, let's talk about some primary TDR terms that you'll find in the technical literature. First one is reflection coefficient. It's the most important one. It's little letter p. The next one is distance to fault. Then we have velocity factor, line loss or cable loss, return loss, RL, load impedance, ZO, and then VSWR. Okay, here's the formula for the reflection coefficient, P. It equals V reflected divided by V incident. So for fixed termination, ZL, P can also be expressed in terms of transmission line characteristic impedance, ZO, and the load impedance, ZL. Now on a matched load, what we have going over here, we can see our original formula right here. And so representing a matched load, a short circuit and an open load, P has a range of values from +1 to -1, with 0 representing a matched load. So when ZL equals 0, the load is matched. V reflectors is equal to 0, thus P equals 0. Now for a shorter transmission line, again, here's our formula up here. A ZL reading of 0 implies a short circuit. The reflected wave is equal to the incident wave, but it is opposite in polarity. So the reflected wave negates part of the incident wave, such that P equals -1. And here's again, here we have our formula. So when ZL is infinite, an open circuit is implied. The reflected wave is equal to the incident wave and of the same polarity. So the reflected wave reinforces part of the incident wave, such that P equals 1. Now finally we have line and load impedance. The characteristic impedance ZL or the load impedance ZL can be calculated with the value of P. So we have that formula right here, so that ZL equals ZO times 1 plus P divided by 1 minus P. Okay, let's talk a little bit about return loss. The return loss of a transmission line is the conversion of the reflection coefficient to decibels. It is always a positive number. It can be calculated simply by minus 20 to the log 10p. So that's it. Here's what every ham station has. They have a VSWR meter. Great device. The voltage standing wave ratio, VSWR, represents the ratio between the maximum and the minimum amplitude of the standing wave. VSWR can be calculated by the following equation. VSWR equals Vmax divided by Vmin, or in this particular case, 1 plus P divided by 1 minus P. All transmission lines have losses. Transmission line losses due to change in frequency are proportional to the square root of frequency. And we know that the bandwidth equals 0.35 over the rise time. Thus, losses can be calculated using a fast transition and narrow pulse as a substitute for frequency. And here's an example of such a pulse. Now, the TDR-CableScout uses a very narrow pulse. This pulse is 400 picoseconds with a rise time of less than 150 picoseconds. This approximates a loss measurement of approximately 3 gigahertz. The loss measurement is the amplitude of the incident to the reflected pulse expressed in decibels. And you can see here's the incident and here's the reflected pulse. If the attenuation of a particular frequency is known, the loss of any other frequency, F2, can be calculated by AF2 equals AF1 and the square root of AF2 divided by AF1, a loss in dB. It's that simple. This last section deals about faults in a transmission line. Here's the basic system. Over here we have the generator, usually a transmitter. It has some kind of source impedance. Here's the transmission line, ZO, and here we have the load. Now when you see the representation of these conditions as waveforms on your oscilloscope, it'll make more sense to you. Ideal conditions were ZS equals ZO equals ZL. That's the ideal condition. Here all the energy is absorbed in the load and everybody's happy. Maximum power is going out to the rest of the world. Here's an inductor fault. An inductor fault is usually indicated by an increase, a momentary increase in impedance. And this usually occurs because you have perhaps a broken shield or a bad connector. Next one is a capacitor fault. That's usually a momentary decrease in impedance and could be because of a pinched cable. So you find that little glitch, find out where the fault is, and you can fix it. This one over here, ham radio operators that I know, not all, have done this. They've taken several pieces of coax, strung them together. In this particular case, RG58, 50 ohms, mixed up with a RG59, 75 ohms, and then you get these kinds of reflections. Here, the opposite is true. You start off with RG75 ohm coax, connected to RG58, and then again, RG50 ohms, and again you get a reflection. Seems to work good, but it's not optimum. Finally, you can measure the characteristic impedance of a transmission line with a very simple device. It's called a variable resistor. So you just adjust this until you get minimum reflections, then measure it on your ohm meter right here, and whatever the ohm meter reads out, that's the characteristic impedance of this transmission line. It's that simple. Okay, here's the basic setup for making TDR measurements on transmission lines and cables. When you first turn it on, the display will indicate the model number. In this particular case, it's a Pro version, and also the firmware version. On the left is the outputs for the scope for pulse TDR on the device under test, on and off switch, trigger out, which allows you to view signals on a sampling oscilloscope because it does have a 100 nanosecond pre-trigger. And in this section right here is your step TDR and the 3 impedance lights. These buttons control the TDR-CableScout. This button allows you to select the cable or the velocity factor. This button allows you to make calculations. These are the up and down scroll buttons. This is the enter key. This button allows you to set the source impedance, and this button lets you adjust the range and duration. The cable velocity factor button allows access to the various cables that are in the library. You can scroll up and down, as you can see right here. And let's select a popular one that we have. You know, OG58 is very common. Here's OG58. That's the cable nomenclature. That's the impedance, 50 ohms. It has a loss of 3.3 dB and a velocity factor of 0.66. The next button sets the source impedance most suitable for the device under test. Right now it is set to 50 ohms for 50 ohm type cables and in step TDR. By pressing it again, we can see that now we have it set for cables between 75 and 100 ohms. Pressing it again, we can see that it's set now to test the transmission lines and cables between 300 and 600 ohms. And finally, we can set it for pulse TDR. This is for checking cable losses and making very fine, high-resolution TDR measurements. This button selects the range and frequency and pulse width. In this particular case, we have a range of 75 meters. The pulse width is 500 nanoseconds. The period is 1 microsecond, and the frequency is 1 megahertz. We can test cables to a variety of distances. For example, here we can test it out to 150 meters. Here 1.5 kilometers. And then finally all the way out to 15 kilometers. By pressing this button right here, the calc button, we can measure the distance to fault, and we'll show you some examples later on. We can calculate the reflection coefficient. We can calculate the velocity factor, and we can calculate the cable loss per 100 foot at 100 megahertz. And let's suppose we're using OG58 cable. We have that already selected. It's 0.66 velocity factor. So we select calculate distance to fault from our calculation choices. We press enter. Here is our velocity factor. We can change it, and we'll leave it at 0.66. Next step is to measure the time from the incident pulse to the fault, and we're doing it right here, and that is about 217 or so nanoseconds. We go back to our TDR-CableScout and dial that number in, 217 nanoseconds. There it is. Press enter, and that's 70.76 feet or 21.55 meters. Okay, now let's measure the velocity factor of the cable. Remember, velocity factor is the speed at which the electrical signal propagates through the cable. We have a 12-foot chunk of OG58 coax connected to the device under test. Alright, we've selected the mode. We have a choice between feet and meters. Press enter. We've already selected 12 feet because we could change that. And then press enter. Now all we need to do is find out what the time it takes from the incident pulse to the reflected pulse. Use our cursor right here, comes in very handy, and we can see it's approximately delta time 34 nanoseconds. We'll dial that into our CableScout using the up and down key. There's 34 nanoseconds. Press enter, and here's our velocity factor, 0.717. Once the TDR-CableScout has measured the reflection coefficient, you can get some additional calculations. Okay, let's do that now. Here we have an incident pulse that has an amplitude of 1.18 volts. Take a look on your scope, and sure enough, here it is, 1.18 volts. So we've already entered that into our TDR-CableScout. The next one is the reflected pulse. It's 0.3 volts peak to peak. And let's see what that measurement is right here. And we can see that it is right there, 0.3 volts peak to peak. So what does that mean? Well, let's do the calculations. Press enter, and we get a reflection coefficient of 0.250. Additional calculations are available by pressing the down arrow key. Here we see that the transmission line impedance is 83.3 ohms. The return losses in dB is 12 dB, and the SWR is 1 to 1.66. Let's suppose it's important for you to know what the cable losses might be in a particular cable you're using as a transmission line. You need to use the pulse TDR mode, and you need to select its output. So we do that. You notice how the light is changing until we've selected pulse TDR. Then we take a sample of cable that we want to measure and connect it to this port right here. We press calculate, and measure cable losses is displayed. We press enter. Now we can use either meters or feet, and we'll be using feet. Our sample is 12 feet long, so the next thing we need to do is measure the amplitude of the incident pulse. And we'll do that right here. And the amplitude of the incident pulse happens to be about 468 millivolts. So we go back over here. And guess what? I've already dialed it in. But that's okay. Here's how you change it. 468 millivolts. Then we measure the amplitude of the reflected pulse. Again, we select it. And that happens to be 212 millivolts. We'll go over here to 212 millivolts. And we press enter. So our losses per 100 feet at 100 megahertz happens to be 8.247 decibels. Okay, that's it for PreciseRF and the TDR-CableScout.